Okay, so real zeros of polynomial functions, these get really fun, and I think they're actually pretty interesting.
I think so too. There's so much to this. Like, there's so much there that we can do with this.
Quite a bit, actually. So let's just dig in, shall we? Has anybody seen Poltergeist? Have you seen Poltergeist?
No, but I think that's what this is from that you wrote on the slide.
Poltergeist 2. Remember long division? It's back.
But it's not as creepy as the Poltergeist probably is.
No, way less creepy. A slight skosh more confusing.
Do they do long division in Algebra 2? Doesn't that get?
It does show up.
Okay. Well,
so this should be mostly refresher, but it still is a challenging concept.
Of course. So what we do is we stick the divisor 3x plus 2. This is how I like to write it, and since I have the pen, I like to write this 3x plus 2, and then we make a little division-y thing, like so.
Wow,
sorry that it went a little wonky there at the end. Why is this 3x squared plus 5x squared? Should that be cubed?
Let's make it cubed. 3x cubed.
Cubed plus 5x squared plus 8x plus 7. So I didn't need all of that room, but pretty close. All right, when we want to do long division, well, why don't you take the wheel?
Well, when I like to do long division, especially with polynomials, I just look at the very leading term under the division symbol there.
This 3x cubed?
That 3x cubed. And I go, okay, what times 3x?
Which we get from over here.
Yep. Equals 3x cubed. So, that's what I ask myself.
So what do I multiply 3x by to get 3x cubed? I think that would be x squared.
I think you're right.
Now, do you write that up above your other x squared?
I like to line them all up.
So
if I've got an x squared, I put it on top of all the other x squareds.
That's how I like to do it too.
Yeah.
Okay.
And then you got to multiply that x squared in red with everything in front of the division.
So the 3x plus 2 both gets multiplied by x squared.
Yes, that is correct.
So 3x cubed. That was the whole point. And then 2 times x squared is 2x squared.
And it's plus 2, so it's going to be plus 2x squared.
Okay, and then you normally do this, right? We're going to subtract these.
Oh, yeah, totally subtract those, just like regular long division.
Okay, because that's what we do when we divide two numbers. We have to subtract each time. So we're subtracting both of these. So 3x cubed minus 3x cubed, that's 0.
Yep, 0, which is what we wanted.
Yeah, that was the whole point.
We don't want anything in that spot when we get done.
Yeah, so 5x squared minus 2x squared gives us
3x squared.
3x squared. And then we have to drop down the next term so that we can continue long division of fun. And then we start over, basically. What do we multiply 3x by to get 3x squared?
Right, and it happens to be x. What times 3x is 3x squared? So in this case, it's just x.
It's just x.
Just x.
So now we multiply x times 3x plus 2, and it goes right here. 3x squared. 2 times x is
2x.
Then we take that and we're subtracting this whole thing.
And notice on both of these, Mrs. Stevenson put parentheses around a thing that we're subtracting. That's super important. Long division mistake number 22 is when you go through and you do all your long division and you forget to subtract both parts.
Right.
Because there's usually several things down there.
Right. What if we were subtracting, but this was a negative on the inside?
Ooh, it's a
we'd
plus.
have to add it. So.
Yeah, so you got to really pay attention.
So 3x squared minus 3x squared is 0. 8x minus 2x.
6x.
6x.
Bring down 7.
We're almost done. All right, so 3x times what gives us 6x?
2.
That's great. So plus 2, and then we come back and we multiply 6x
plus 4. Yep.
We have to subtract. So 6x minus 6x is 0. 7 minus 4 is 3. And so we can't divide anymore. This becomes our remainder. And this is how we write our remainder. We write it as plus 3 over whatever we were dividing by.
3x plus 2.
Right. So this that we have written, what is this form called? That's the...
That's right there. It says right there, a summary statement.
Okay, this is our summary statement.
Yes.
Okay, that's what this is. That's one way they can ask you to write it. The other way they can ask us to write it is this other way, but there's like a word for it.
Yeah.
Okay,
we'll know when we come to it.
This is the first way that you write it, and then here's the second way for you to write it, and just the instructions tell you to write it both ways, so write it both ways. What we do is we say f of x equals what we were dividing by, which is 3x plus 2, times what we got without the remainder, and then we just add whatever the remainder was.
Yep.
That's what r of x would be. So this is the second way to write your answer. And the reason that they're writing it this way is because we're kind of connecting to the fact that when we divide by this polynomial 3x plus 2, we're saying we could factor this into 3x plus 2 times x squared plus x plus 2, but we have to have this random plus 3 over there as a remainder.
Right, because that's what's left.
Yeah, so, all right.
Okay, so more polynomial long division.
More polynomial long division. This is where it gets fun.
And exciting.
Yeah, so we've got this problem here, and we want to divide these things. So I'm going to write 2x squared plus x plus 1. That's my divisor. Now, whenever we write our dividend, isn't that what that's called?
I don't know.
Okay.
It sounds good.
Okay, 2x to the 4th minus x cubed.
I know what comes next.
Yeah?
0x squared.
Right. We have to put placeholders
0x.
for any term. Like, these have to count down. We've got an exponent of 4, an exponent of 3, an exponent of 2. Now we need an exponent of 1, so plus 0x.
Minus 2.
Then the minus 2. So that's really important, otherwise you don't get the same
Long
answer.
division mistake number 27 is forgetting the placeholders, and I'll tell you what, we're both guilty of that, even as experienced mathematical
Every
people.
now and then it happens.
So
it
just whoops us. So you got to pay attention.
All right, so we want to figure out what do I multiply 2x squared by to get 2x to the 4th?
X squared.
Sorry, x squared is correct, and so let's put this over the x squared. And then we have to go back and multiply all of this stuff.
Yeah, everything.
Everything. One of these days, Dr. Pepper's going to call me and be like, we want to give you money for all the times that you've put a Dr. Pepper can in your videos. I doubt that's going to happen. That makes me nervous. I'll probably spill it on your laptop. Okay, so, but we're subtracting this.
All of it. So make
Don't
sure
forget.
you put it in parentheses, because you're subtracting not just 2x to the 4th, but everything behind it.
Everything. Okay, so 2x to the 4th minus 2x to the 4th, that's
0.
good. Negative x cubed minus x cubed.
Minus 2x cubed.
Okay, see, that's where we would have had an issue if we had not remembered to subtract.
That is correct.
0x squared minus x squared.
Minus x squared.
Okay. Now drop one more down because we have 3 terms over here, so we're going to need 3 terms to divide into. Okay, and let's go again.
Negative x.
Okay, so 2x squared times negative x gives us negative 2x cubed. I agree with that. Multiply.
Minus 2x cubed. Minus x squared. Minus x. Danger alert here if you forget your another place to go wrong, if you forget to subtract everything.
Yeah, because if we have negatives and we're subtracting, those switch to positives.
That is correct.
So it's like ching ching walla walla bing bang.
Yeah, click click.
Yeah, click click. So negative x squared plus x squared. Can I go ahead and mark it? Is that
I mean,
okay?
that's, yeah, sure.
I mean, if we wanted
Ready?
to, we could just
Chitty
bam,
chitty bang
bam,
bang. Chitty
bam,
chitty bang bang. Chitty
bam.
chitty bang bang.
Okay, now
All
this I feel much more comfortable. Okay,
All
those
right.
canceled out. Wow. And that leaves us with just x there. Bring down your next term. I can't multiply 2x squared by anything and get x.
I can't either, so
that means we're already at our
we're done.
remainder. So we have plus x minus 2 over 2x squared plus x plus 1. And normally, like, if we only have a binomial that we're dividing by, 2-term, then we'd only have one thing on the top of our remainder. But since we're dividing by a 3-term, it's okay that we had 2 on top. So this is one form that we want to write it in, and the other form that we want to write it in.
I know what it would be.
Okay, what would it be?
2x squared plus x plus 1.
2x squared plus x plus 1
times
times,
x squared minus x
okay,
plus x minus 2.
right. And if you get confused on that, look back at your slide before this, because you take what you divided by, and then your answer, and then
Plus remainder.
Plus the remainder, yeah.
Yep.
It's all there. All right, Ms. Reyes, had to go somewhere and I got tired of waiting on him, so here we go. The remainder theorem. If a polynomial f of x is divided by x minus k, then the remainder is r equals f of k. What this is saying is if we wanted to divide by like x minus 2 into this, the remainder at the end is the same thing that we would get if we did like f of 2. So let me write that out. This is going to give us, if we divide by x minus 2, this is going to tell us what f of 2 would equal. So we're going to do it. I got tired of waiting on you, so I started. Okay, we're going to do synthetic division, which
I love synthetic division.
it's the best.
Makes life super nice.
What you do is we take the opposite. This is a factor. Like you normally see this like in a parentheses situation. We take the opposite of that number.
Take what makes it 0.
Take what makes it 0. So that would be a positive 2. And then we take the numbers, these coefficients right here, we line those up.
Yep.
Is this the way you normally set it up?
That's perfect.
Okay. All right, so what we do is we always drop the first number.
Bring down.
Bring down the first number. Then we multiply 2 times 3. And
Multiply.
We get 6. And then we add, coming down in our column. 7 plus 6 is 13. Multiply,
And then repeat.
Yeah, multiply this diagonally. 2 times 13 is 26. Add, coming down, negative 20 plus 26 is 6. So the remainder theorem says that f of 2, because we did 2 in our synthetic division, the f of 2 is 6.
Correct.
And that's what it's asking us about.
Right. Bring down, multiply, add, repeat.
Yeah.
Every time.
Multiply, add, multiply, add. It repeats all the time.
That's what I said.
Yes. Okay, so now we're going to find f of negative 1 by talking about dividing x plus 1. So,
Coefficients.
yep.
Now, I will tell you, if you get a sign wrong on your coefficients, it'll totally mess you up.
That's true, yeah. Totally true.
Happened to me on a college test one time. I still remember. It was brutal.
That's
Like I
terrible.
knew what my answer should have been, but
But
I
you
was
just-
missing a sign. I had the wrong sign listed down in it. And that's one of the things about synthetic division too that's so nice. Sometimes you can tell what you're supposed to get, like you know what you should get.
Right? So you know if you did something wrong?
Yes. Now, like on this case, we're still learning how synthetic division works. We may
Right.
not be able to tell right away, but we're approaching a point where when you do synthetic division, you should have an idea of what you should get.
Right. So
Hey, we got a 0 there.
we got a 0. And that's also going to end up meaning something. Whenever we divide by x plus 4 and we end up with a 0, that means that I can factor 3x squared plus 7x minus 20 into x plus 4 times something.
Right.
And also the thing that I'd like to mention real quick, because let's say you're doing synthetic division and you're actually trying to divide, you have to realize that if I divide by x minus 2, this is really 3x squared. No, not x squared.
3x.
Sorry. See, that's why we're talking about it. It's always 1 degree less than what we
Right.
started with. We started with x squared, so this is 3x.
Right. 3x. 3x. Yeah, tap the pen. Tap the pen.
3x.
Plus 13.
Plus 13 plus our remainder of 6 over what
X
we
minus
divided
2.
by.
Yep.
So, and we could do that in each of these cases. So on this last one where it divided evenly, we're saying that 3x squared plus 7x minus 20 can be factored into x plus 4 times 3x minus 5.
Right.
If you FOIL that out, I bet that's true. That's not what it was asking us. I just thought it was worth mentioning.
It is worth mentioning because that's where we're headed.
Yes, that is exactly where we're headed
Yeah,
right now.
okay.
Just
All right,
keep
here we
going.
go. You heard me.
Okay, 2.4 still. We've got all these words.
A
What
lot
do
of
they
them.
mean?
If polynomial function, that shouldn't be too hard. F of x has a factor x minus k if and only if k
F of k equals 0. When you plug in k, it should equal 0.
Yeah.
That means it's a factor.
Which is exactly like the last example on the previous slide.
Right.
So the x minus k part, we're interested in what k equals that makes a 0 with x.
Yes, we are. All of these things here, this 1 through 4, all of these things are saying the same thing.
Which we've talked about, we've kind of dropped off hints along the way if you've
Yeah.
paid attention. So
X equals k is a solution or root of the equation f of x equals 0.
k is a 0 of the function of f.
K is an x-intercept of the graph of y equals f of x.
And x minus k is a factor of f of x. These are all saying the exact same things.
Yeah, so let's try it out here with 3x squared plus 7x minus 20 divided by x plus 4. If they ask us to show that that's a factor, we just got to do some nice division to show like some synthetic division.
I would use synthetic division. You could use long division. You could use synthetic division. You get to pick it, but synthetic, in my opinion, in this case, is the way to go. Yep.
Okay, and so we switched the sign here because this is not x equals something. If we wanted to write this x plus 4 as x equals something, we'd really be setting it equal to 0, right? And we'd solve, and we get x equals -4. That's why this is switching signs. If they had told us, hey, check to see if x equals 3 is a 0,
right,
we wouldn't change the sign.
No.
Okay, but they didn't do that. They gave us a factor,
right.
so we switched the sign.
Or think about the x value. Just think about what you have to add to +4 to make 0.
-4.
There you go.
Is this what we just did on the left?
Bring it down, multiply, add, and...
Oh, look. This is indeed a factor. And we just proved it because we got 0.
We got 0.
If we didn't get 0...
Is that the last example?
I think that was the last example.
Shut the front door.
I'm not sure, though.
Was that what you were saying?
I was trying to ventriloquist that up.
Yeah.
I don't think they even heard it.
They probably didn't, but
Probably
check it
not.
out, which is what we mentioned on the previous slide. Synthetic division.
Let's do it.
Hey, let's take, x minus 3. We're going to run it through 2x cubed minus 3x squared minus 5x minus 12.
Remember, we would switch the signs because we're dividing by x minus 3.
Totally sign switching occurs here.
So take the coefficients. Hey, if they skipped any, just like with long division, like if that x hadn't been there and they skipped it, we'd have to put a placeholder of a 0.
Yep.
Just keep that in mind.
And those slip in on you. Especially with synthetic division, it's a little more difficult sometimes to catch that one.
Yeah, you'll be going along just fine, and then all of a sudden they'll throw one in where you needed a placeholder, and then you won't realize it until you miss that question on a quiz or a test, and by then it's too late.
And it would happen on a question like this where we're told that maybe something was actually a 0 of a problem, and when you get done doing your math and your synthetic division here, then you would get not 0 at the end, you would get another number.
Right, that'd be terrible.
Right, and so pay attention.
Yeah. So the answer to this then, we start 1 degree less than x cubed, so it would be 2x squared plus 3x plus 4. There is no remainder, which means like this is our answer, right?
Yeah, I'm pretty sure that's saying there's no remainder.
And so since there wasn't a remainder, keep in mind that means that we could write this as x minus 3 times what our answer is. We could write that original polynomial.
Just like that.
This right here, this we're saying factors into this.
Those two things, yep.
Brilliant.
Brilliant. Did you wanted to start?
No, you.
I think this is fascinating.
This right here?
Yes.
Fascinating.
Super.
Okay, we've got a couple words here that are important. Rational versus irrational.
Okay, rational means that you can take a fraction and put one number over another and get like a fraction.
Okay, rational zeros are anything that can be written as a fraction.
That's
so
what I just said.
Any normal number like 5 or 6, those can be written as fractions because it's over 1.
Right.
Or 2/3, 5/6, all those are
repeating
fractions.
decimals?
Repeating decimals, like 0.3 repeated. That's the same as 1/3. So,
it's rational.
Irrational zeros.
I know. I know
Okay.
what non-ending, non-repeating decimals, like
just
square
read
root
that.
of 2.
Yeah.
Oh, I did not read it. I was looking over there to the side. Non-ending, non-repeating decimals. So
like
pi.
the square root of 2. Or pi, or whatever.
Yeah,
okay?
that's
those
irrational.
Those are irrational. But
Can't write them as a fraction.
rational is like 2, 3, 5, 6.
2/3.
2/3. You know, things like that. Okay.
Okay.
There's this theorem that says if we've got this polynomial here, then we can write all of the possible rational zeros by taking whatever our last coefficient is, which is p. That's what this is saying. P is an integer Okay, from Ava. If we take the factors of the last coefficient and put them over the factors of the first coefficient, which is Q.
So what we're saying is, when you're looking for a 0, this won't give you those really goofy, weird decimal answery zeros.
Like square root of 2.
Like square root of 2 or some kind of really weird decimal. But it will give you a specific, if there is one, a specific value that can be written as a fraction.
Yes. So like on this example down here, I asked what are the rational zeros of this? Well, what we can do is we can list out all the possible rational zeros. This one's kind of boring.
Yeah, it's pretty easy actually.
We take all of the coefficients of the last one. All of the factors of the last
What
thing.
times what is 1?
1.
God, that was hard.
That's the only one. And we put it over the coefficients of the very first one.
What times what is 1?
1. Okay, so in this case, like normally we would have multiple things on top and bottom and we'd have to match them all up, but in this case we've got 1 over 1, which is just 1.
Yeah.
That's the only possible rational zeros for this is positive and negative 1.
Yep.
It wants us to figure out what they are.
Yeah.
So let's use synthetic division.
Definitely use synthetic division.
We can check to see if 1 is a rational zero of this by putting it in with synthetic division. So keep in mind here, I've got 1, negative 3. Oh, there's not an x there, so I need a placeholder.
Mistake number 27.
That could have happened just there, right there. Okay, so we're checking to see if this is a
Bring
rational
down,
zero.
multiply, add.
If it
Multiply,
is,
add.
if it
Multiply.
is,
Add. Oh.
oh, this one's not a rational zero. Oh, man. Okay, let's try negative 1.
We have to do it again?
Yep, we have to do it again.
Oh.
Can you imagine if we'd had more than 2 possibilities?
Oh.
And you always stick a plus or minus on these. Like, no matter what you've got, you always stick a plus or minus.
Because those are the possibles. Like negative 1 times negative 1 is positive 1. Oh.
What terrible thing is going to happen?
Oh, no.
What is this? Neither of these
Oh.
are rational zeros?
Wow.
Did
wow.
we do something wrong?
Let me just check the old book here.
I just can't even believe that we wouldn't get
Just
any rational zeros.
Just looking, and I think that there was these 2 guys.
Oh, nope, not rational zeros.
We wrote the problem down right. That's important.
So there's no rational zeros.
However, we do know for a fact that this graph does cross the x-axis at least one place.
And we know that because
it's an odd degree polynomial.
Odd degree polynomial. Because of that 3, it has to go through the x-axis at some point. It just has to.
It has to.
Its range is negative infinity to positive infinity.
Right. And it turns out that this has to happens to be irrational.
So, yeah.
Hey, okay.
Go ahead.
So we're looking at finding a rational zero there.
Finding the rational zeros.
And we're doing just a little slight skosh cheat ahead to make sure that we've got some rational zeros. And it looks like perhaps we do this time. So we're going to charge ahead here. And with this particular example, finding all the factors that multiply together, we get a little bit more of a busy look. Because now instead of just having 1 over 1, we're going to have a few numbers.
Right. So what we're going to do is we're going to pretend like we don't have our calculator. Because if we had our calculator, we could just find all of these zeros using our graphing calculator.
Hey, guess what? On a test, you're going to have to do this without one.
Yeah, so we're going to walk through it as though we don't have it.
Right.
So that means we have to list out first the possible rational zeros.
Yes. So all the possible rational zeros. And what we're going to do is we're going to start with that negative 2 at the very end and think of all the things that multiply together to make a negative 2.
Well, I'm going to go with 1 and 2.
I also will choose those.
Okay.
So
plus and minus 1, plus and minus 2. You just stick a plus and minus with whatever you get.
Yep, always.
Okay, and then that's over. So it's the last one over the first one.
Plus and minus 1 and 3.
And so what we do is we're trying to put these together now. Everything on top has to go with everything on the bottom. So like plus or minus 1 over plus or minus 1.
Which would be plus or minus 1.
Right. And then what do we want to do after that?
Well, let's go 1 over 3.
Okay, 1 over 3.
Which will be plus or minus 1/3.
Okay.
And then
now take the 2 and put it over the 1.
Right.
So plus or minus 2 over 1, which is 2. And then
lastly, plus or minus 2 over 3.
So that's, if you count them with the plus and the negative, that's 8 possibilities.
Eight possible checkings.
So here it sounds bad, but as long as we can get the first one, then after that it's not so bad.
No, right. We just, right.
Yeah, so I like to start with 1 and -1 as my first
Oh,
go-tos.
always. They're usually the easiest ones to work
And
with.
they end up being ones a lot.
Right.
Okay, so 3, 4, -5, -2.
And if it doesn't work for one, we're just going to try another
just
one.
gonna keep
I mean, we
going.
just keep
Because
going.
we don't have a graphing calculator sitting
we
right in
don't.
front of us
Right.
on my desk. We don't.
On my desk, actually.
Yeah, no, there's not one on his desk.
Now, sometimes too, when you start doing this, you can tell pretty early on if something's going to work out or not. Like, for example, this one worked out, but let's say when we were right here with -5 and 7, and we put those together and got like 22. Well, there's no need to go further because
You're
1
not
times
coming
22
back
is
from 22.
yeah, you're committed.
Yeah. So we figured out, hey, 1 works as a 0. And so now we could go one of two ways. We could go back and start trying more of these, or we could say, well, this is 3x squared
Yep.
plus 7x
Yep.
plus 2.
Right on. Preach it.
We could set it equal to 0.
Yes.
We could factor this.
Yes.
And then we've got our other rational zeros without having to guess.
Right. But let's practice.
Okay.
No, you don't want to? That's fine.
I
we
mean,
don't have
we
to.
can practice if you want. I mean, I could pick randomly out of thin air -2.
Do it.
Okay.
All right.
Okay.
So what we're going to do is we're just going to run synthetic division again because every now and then you do get a problem that isn't necessarily third degree, which lets you factor quick
Right,
and easy.
right. If it was 4th degree, we'd have to do it
Right,
at
we'd
least
have to do it again.
twice.
And here's the thing: don't go back to the starting point when you have to do this more than once.
No, use what you've already got. We know the 372 works.
Right.
So start from there.
So
I'm not sure if this will work.
I'm
Maybe
thinking,
did I guess right? Oh, look, beautiful guessing.
You are a genius.
Thank you. Thank
when
you
they
so
handed out
much.
genius cards, did you get 2 of them?
I was absent that day at school.
Oh, so only 1.
Yeah.
All right. Well.
All right. So if we think about this as factors, we know that 1 is a 0, so that's x minus 1. We know that -2 is a 0, so that's x plus 2. And now we have this last factor, which is 3x plus 1.
Bingo, bango, chitty, chitty, bang, bang.
But they want the zeros.
Right.
So this is x equals 1, x equals -2, and this is x equals -1/3. Because we subtract the 1 over and then divide by 3.
Right.
There's our rational zeros. Now, okay, I have to be honest with them. I have the graph right here in front of me, and I was using that to help me.
So disgusting.
So, and you can do that too. On your homework, just ignore him. We already worked this out. I don't know what he's pretending about. Okay, on your homework, if you want to graph it so that you get an idea of which ones to try, that's fine. Just keep in mind that on a test, we might give you one that has a few limited choices for rational zeros, and we might expect you to try them until you get it. Okay, that could happen on a test. So be prepared.
Hey, so we were talking a minute ago about trying to narrow down the list of possible rational zeros to check, and here's a couple of rules that are huge time savers.
Yes.
Huge.
Okay, so we're going to talk about upper and lower bounds. Now, this has nothing to do with the boundedness that we've talked about.
On a graph. This is not talking about a floor and a ceiling that a
No.
graph doesn't go through.
What this is saying is that we can call a number k an upper bound for the real zeros of f if f of x is never 0 when x is greater than k. Or it's a lower bound if the opposite is true. So can I draw a picture?
Yeah, draw a picture.
Okay. So if I have like a graph, and let's say it's a cubic function. This is a nice looking cubic function.
It's a good looking cubic.
Okay, what it's saying is that there's some value over here that we can call a lower bound.
And when we check this value with synthetic division, we'll get a certain pattern for an answer.
Right, and so instead of having to like mess with your window on your calculator a whole bunch, what you can do is you can say, okay, well let me check this number, this upper bound, and see if it's really an upper bound. And if it is, then there's not any zeros to the right of that point. Or you can check the lower bound, and if it is a lower bound, there's no zeros to the left of that point. So the pattern for the upper bound down here is that when you do synthetic division, all of the entries should be non-negative.
Positive or zero.
Positive or
Zero would
zero.
be included as non-negative.
Okay, so it just has to be non-negative. If it's if we're talking about a lower bound, then it alternates non-negative and non-positive. And so that typically will end up being like a positive number, a negative number, a positive number, a negative number.
But again, non-positive could include
It could have a zero. So, but I don't think they're that mean.
I don't think they are either.
Yeah,
and,
so you should see alternating positives and negatives.
And this is really a great tool to narrow down. So like if they give you a rational, you're trying to find rational zeros and they pop a 24 in there with all the things that make 24, this can help you narrow down your choices.
Definitely.
Yeah. So we'll show you how to do this on the next slide. How's that sound?
That sounds great.
Okay, let's do it.
Okay.
Hey, let's check out how to use those upper and lower bound limit tests here.
Yeah. Okay. So it's asking us to prove that all of the real zeros for this polynomial lie between -2 and 5.
Oh, they made it so easy.
We need to check and see if -2 is a lower bound, and then we're going to check and see if 5 is an upper bound. We'd use synthetic division to do this.
Make sure you list all the descending powers of x.
Yes, don't skip any.
Don't skip any.
All right, so synthetic division.
All right. We know this probably won't be a 0. We're cool with that.
That's not what we're hoping for here.
We want numbers here. We want numbers all the way across. Now, we can stop right here if this was real life. If we were looking for 0, like I know that no matter probably what we do, times that whatever we get, we're not going to end up with a 0.
But that's not what we're looking for.
But that's not what we're looking for. So we keep going. Keep going, Mrs. Stevens.
I just had almost made a terrible error in my math.
Well, we don't want
I may
terribles.
have still made a terrible error, but not so terrible that this is not still the case.
That
we
looks
have
correct.
We have alternating
opposite signs.
Positives and negatives.
Non-negatives.
Non-positives and non-negatives.
Yes.
Alternating.
Yes.
So -2 is a lower bound.
That means that the 0 for this function has to be between -2 and 0.
Yeah. That's it?
Yeah.
There has to be a 0 between -2 and 0?
Well, not necessarily, but there's not one past -2.
There's not one to the left of -2.
Yes, that's what I said.
I will agree with you there. Okay. Now let's try 5.
Hey, let's try 5.
Let's try 5.
Okay, for reals.
I'm trying 5.
Do it right now. Yes, and use a green color because green's pretty.
Excellent choice. Make sure you add correctly here. We don't want to whoops. And again, if we were looking for a 0, by the time we get here, we can stop.
Yeah.
Because 5 times something else, we're not getting back to 0 anytime soon. Holy guacamole. 129 times 5. Who puts that there? 645.
Is it really 645?
5 times 129 is 645. I don't know where you got 245 from because that is not
I was trying
correct.
to do it in my head.
You were really close, though.
I just carried badly.
That's okay. It happens to the best of us, Mrs. Stevenson.
Well,
653 is what your answer should be.
Okay. So here what mattered is that they were all...
Non-negative.
They're all positive. So 5 is an upper bound.
5. That means, in other words, for this particular problem, we're going to have zeros that have to be between -2 and 5.
That's where they all have to
cannot
be.
be outside of that interval.
But since this is an even power, there might not be any zeros at all.
So if they do exist,
they have to be between -2 and 5.
but they may not.
Exactly.
They could be imaginary.
But let's not talk about that.
Okay,
yet.
we'll save it for a later.
Yeah,
later
save it
day.
for later.
Okay,
Yeah.
good talk. Whew, man, my hand. It's tired, getting hand crampy.
You're not doing anything.
Watching you is giving me hand cramps.
Okay, we're gonna find all the real zeros
I feel another hand cramp coming.
of this thingy, this polynomial right here. Let's do this. Okay. Well, let's start off by listing the possible rational
Let's do it.
zeros.
So the things that multiply together that make an 8 would be plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. Whew, man, I think that's the fastest I've ever said all of those at one time. Thank heavens this isn't 24.
Yeah, 24 would be a nightmare.
And then plus or minus 1 and 2.
So remember, it's the factors of the last one over the factors of the first one. So that gives us all of these that are possible. Let's go.
When I do this, I always start from left to right on the top
Okay.
and just put it over everything I can on the bottom.
Okay, so like plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8? Because they're all over 1? Is that what you're saying, or is that not what you're saying?
That works excellently.
Is that not what you
That
were
wasn't
saying?
quite what I had in mind. I was
Oh, so
thinking
you
of
were
like
gonna go like one
I was
half.
gonna, yes, that's what I was going to do. But
Okay.
you know, either way,
Yeah.
whatever method you feel comfortable with, stick to it so that you're sure to list everything.
Now, what's great is okay, so we have 1/1,
That's
and then
1.
1/2, which
Yeah,
is
that's
1
a half. Yep.
2/1 is 2.
Yep.
2/2,
Hey, that's 1.
which we've already got.
I already got it.
And then 4/1 is 4.
Yep.
And then 4/2.
That's 2.
We've already got it.
Yeah.
And
8/1.
8/1.
All right. And then 8/2
is 4. We've already got it. Hey, we only ended up with like a 1/2, which is
So
better
that's
than
10
I thought.
numbers to check. We have to check all 10 of those numbers.
Well,
and by
do
the
we?
way, calculator off this time.
Yeah, no, we're not gonna cheat this time because apparently
And when she
That's-
says we, it's all her. Okay.
1. I'm gonna start with a 1.
You know, always start with 1.
Might as well.
I mean, it's
It's
always
easy to check, and we're looking for an upper and lower bound limit. So if we can eliminate some possible numbers
That
here,
would be awesome.
that would be super groovy. I feel like if this isn't a 0, we're going to have to get bigger. 13. Oh, what did we learn from this?
Nothing.
Nothing at all.
Because there's no pattern here. Okay,
None.
that's not helpful.
That's
Now where do we
that's
go?
terrible. Well, let's try. You know what? Let's just try it. Let's try positive 2.
Okay.
That's it's a good round number. Did we list all the zeros off? Did we list everything off? Do we know that we've got the right amount of things up there? 2,
I
negative
guess.
7, negative 8,
You're the one that was
14,
supposed to be
and 8.
like checking while I was writing.
You know, I just was
What you doing there?
nothing. Just double checking. It's always good to double check.
Double checking what?
Make sure that we're set up to good to go, because this is one of those places where you should know that you get a correct answer.
That one didn't work.
Oh, darn it!
What do we want to try now?
I guess we're up to 4.
Okay.
I'm having some good thoughts about this one.
Hey.
yes.
Check that
we
out.
have a 0.
Okay.
So now here's the cool thing. We can start with what we just ended up with
Right.
for our next bit of synthetic division.
Right, that's true. Now, I would like to point out that this thing could be factored now.
Go ahead.
Okay.
By all means.
Because I think we've practiced the whole rational
Yes,
zero thing.
I agree.
If we did not know that this could be factored and we didn't want to try, we could just continue guessing. But this is 2x, what is it?
Cubed.
2x cubed plus x squared.
Yes.
Minus 4x
Right.
minus 2.
Yes.
We can factor this in a way called factor by grouping, and
Shut
we
the
haven't
front door.
we haven't talked about it this year, so that's why I wanted to bring it up because it's a pretty handy way of factoring.
No way.
Yeah, no, really.
Get out of town.
It's a great way. Okay, what you do is you look at the first 2 things you've got and you try to see what you can pull out of that.
X squared.
Okay, and then what is left over?
2x plus 1.
Okay. Then you look at the next set, the negative 4x minus 2, and you say, what can I factor out of that?
Negative 2.
Negative 2, and then what is left over?
2x plus 1. Oh my good, look at what's in there.
What we want to have happen is that this this part is the same in both, which means we can factor that.
Oh my cheese.
Did you say cheese?
Cheese with a J.
Okay. We put one set of 2x plus 1 in front, and then what's left over, this x squared minus 2, gets stuck in another set of parentheses.
Then you can set those equal to 0.
And solve.
And solve, which means that we're going to have 2 irrational, looks like 2 irrational numbers.
2? Oh, yeah, 2. Okay, yeah. Yeah, I'm with you.
Yeah.
The first set of parentheses, 2x plus 1 equals 0, you subtract 1 over, divide by 2, so you should get x equals negative 1/2.
So if we had started with negative 1/2 in our synthetic division,
we would have gotten it a lot
0.
faster.
Yeah. Okay.
But synthetic division with like fractions is
It's a little more challenging.
Okay, if we want to do this one, add 2. So x squared equals 2.
Take the square root of both sides.
Now, whenever you take the square root in an equation, you have to put
Plus or minus.
plus or minus. If the book has a square root, that's fine. But if you personally, you right there, sitting at home, at your computer, if you take the square root, you have to put a plus or minus.
Or the math gods will
Tell you that's a wrong answer.
They will, yes.
So we had
Wreak havoc.
this right here was a 0.
Yep.
that 4, negative 1/2, and then positive and negative square root of 2. And I think in the book it has you labeled them as rational or irrational. Oh, I almost messed up again. Okay.
Irrational, like when you get in trouble for coming home late on curfew.
And your parents
And your
are.
parents are
I would
angry?
say your parents are being rational,
Oh.
just in case they're listening.
Oh, totally rational. Yeah, be on time.
Just wait. Whenever your kids are old enough, you will
They
be
won't.
totally irrational.
I will be the most sane person around.
These first two are rational because you can write those as a fraction. And then this last one right here, I'm bad at the curly brackets upside down. So that's irrational because it's a square root of 2.
And when you get one irrational answer, you're going to get 2 irrational answers.
They always come in pairs.
Always.
Kind of weird.
Yeah. They like to hang out together.
They like to hang out together, yeah. So they come in pairs.
Um,
I think that's the end.
oh, yes.